Another effect of deep submicron in CMOS devices is that the noise is also worsened. So we will have a separate lecture on noise, but we can anticipate that what happens is that when we have a transistor that it is biased at a particular biasing point, operating point, there will be some noise current flowing from the drain to the source. Okay, and then that current, it is proportional to 4 kT, Boltzmann constant, absolute temperature, so there will be how much energy do these mobile carriers have, mobile charge have, and there will be some factor here that this gamma, that it is around 2/3 for long channel devices, and this term GD0, that depends on the transconductance. For long channel devices, this is equal to 1, so we can do very quick calculations of this noise current. Now this term alpha changes. It is dependent on this rho that we talked a little bit before. EC is the maximum lateral field, L is the length, so it's going to change with the length and on the amount of inversion, the VGS minus the VTH, depending on the biasing that we have over the gate. So this alpha, it is going to depend on all these parameters, and it is going to get worse. Okay, so we have that for short channels, alpha is lower than 1, so it means that this value will increase. But also the value of gamma, it is higher than 2/3 for short channel devices, and that should not come as a surprise because we have our transistor here. The shorter the length, the easy for the noisy charge to go from the source to the drain or drain to the source, just to jump if they have enough thermal energy. So there will be more noisy. In a long channel device, it will be much more difficult that they just go all the way from the source to the drain. So this should not come as a surprise that the short channel devices are a little bit more noisy than long channel devices. So as mentioned before, we will have a separate lecture on noise who will discuss all these aspects more carefully. But for now, what is important is that the short channel devices noise get a little bit higher. Then the next topic is parameters, important parameters in a transistor, how to characterize our transistor. We have mentioned that we have our transistors here, and then we have to bias our transistor to a particular biasing point, that it is to put it. We have the curves here, VDS, EDS. We have to select a particular biasing point for those transistors to work. But how do we select? First the dimension of the transistor and then the biasing point. So we have some tools that are going to help us do that. Those are the characterization tools. And one of the tools that it is very important, it is the GM over ID and the transit frequency. So we're going to study these ones in detail. So for the first one, we have that we have that the transconductance, as we saw before, is in weak inversion it is equal to Ks multiplied by the ID divided by the thermal voltage. Okay, and so the transconductance grows linearly with the current, and then we also have that this is in weak inversion. In a strong inversion, the transconductance it is equal to 2ID divided by VGS minus VTH. Okay, so this is one of the equations that we have, but we have also another equation in which we have some factor here multiplied by that depends on the sizes and the mobility multiplied by ID. Also we have another equation here, and then it grows only with the square root. Okay, so in a strong inversion we have that the transconductance, that it is a parameter that amplifies the signal, grows much slower with the current than with strong inversion. So we can create a figure of merit that relates the transconductance and the current, and then to see which amount of current I will want to put in my amplifier. So when we divide GM to ID, so we have for the weak inversion, it is very simple because it is just S divided by the thermal voltage, and yeah, this Ks, as we mentioned before, it is around, Ks is around 2/3, so it can be between 0.5 to 0.8, but we can take around 2/3. So this will be around 2/3 divided by at room temperature around 25 millivolts. So that will give us around 26, 27, a factor of around 27. Okay, and then when we start increasing the current, then we will have that for strong inversion. This will go down to GM divided by ID equal to 2 times VGS minus VTH, and then it will depend basically on the amount of VGS minus VTH that it is growing to get current. So this is growing with the current, and then we will see that what we see is that the transition between the weak inversion and the strong inversion, the curve of GM ID divided by ID start doing the following transition here, and then it goes down, there it goes down. So this will be weak inversion, and then when it goes down like this, it will be the strong inversion. Now why is this important? And think about this. When you put some current, then it is going to create some power consumption. You really want to give amplification back. Okay, you really want that your transistor amplifies signal. If you put a lot of current and then you don't get amplification, then you are wasting the power. So in principle, we will not want to work in regions in which we have very low values of GM divided by ID. Okay, so we will not want to work in this one unless it's strictly necessary, and we're going to explain in which cases we will have to go to this to these regions. But we will want to work actually in the lower part of this curve, where we have very good GM over ID. So we have very good amplification for the current that we put. Okay, so that is the places that we will want to work. And for that we have this GM over ID, and you are going to make this template in as part of the laboratory. I'm just going to show you now. Okay, so we have already scripted in Notion. I send it to run. So now we're sweeping the current, and let's see, it's finishing very soon. Okay, so we have here the GMD over ID. So let's see. So we're going to put this in a logarithmic scale. This going in logarithmic scale, and then we can just leave this one like this. Okay, so we can see the GM over ID versus IDS, how it works here. Put the markers with M, and then we can track what is the amplification efficiency of the transistor depending on which bias I put. Okay. That will change if I change the dimension of the transistor. If I put a larger width of the transistor, width divided by length, this curve will move to the left. If I make the transistor smaller, it will move to the right. So this curve is very interesting because it allows us to see what is the efficiency that I have of transconductance with respect to the current that I put to bias. Okay, so this is one of the parameters that I will be pretty much interested. Then I have another that it is also very important, and it is the transient frequency ft. Okay, and for the transient frequency, we're going to analyze very quickly when we have our transistor here. We're going to draw transistor small signal model. Looks like this: CGS, CGD, sorry, CGS. This will be BGS, GM, BGS. There is an output resistance RDS, and then when we connect current source here, we call it this current source current here, we can calculate what it is the current gain that we have. For current gain, as we saw with the ABCD parameters, the current gain, we short circuit the output. And then we calculate the current that goes out here. So if we short circuit the output, this resistor disappears, and then we see that basically what we have is that the input current IS gets multiplied by all the impedance that we have in this node. This short circuit makes sure that this is grounded. The voltage here is 0, so we have CGS in parallel to CGD. So IS is multiplied by all the capacitance that we see at that node. CGS plus CGD, and then we have this voltage. This is the voltage VGS. VGS time GM. This is all the current that it is flowing here. And it is all the current that is going to flow through this short circuit, but with a different sign. So this will be EO. EO is going to be equal to minus this. Then we have that the current gain it will be equal to EO divided by IS is going to be equal to minus GM divided by the omega CGS plus CGD. Or we just want the absolute value, that will be GM divided by omega CGS plus CGD. Now we're going to define the transit frequency, and if we plot this in the frequency domain, we will see that at the very low frequencies this is going to be very, very high, and then this is going to drop another particular frequency. It is going to cross 1 or 0 dBs here. Okay, it's going to cross this value here. That is the frequency that I will call FT. And then I can calculate this exact frequency, making this equal to 1. So we have that 1, it is equal to GM divided that omega T CGS plus CGD, and then we have that omega T, it is going to be equal to GM divided by CGS plus CGD, or FT is going to be equal to GM divided by 2P CGS plus CGD, and then we will call this one the transit frequency. The transit frequency, and then we see that the transit frequency is proportional to the transconductance, and then we can plot this as a function of the current. Then we saw that for very small currents in weak inversion, the transconductance grows linearly. So we plot the transit frequency here. The transit frequency will be growing with the current. So we can see it in a different way. This point and the whole curve is going to move towards the right if I put more current in this transistor, because the transconductance will grow. Okay, so the same information I have it here. I'm increasing the current, and then the transit frequency will increase. And what the transit frequency actually tell me? It is the performance of this transistor at higher frequencies. So the FT tells me that this transistor will amplify only up to this frequency, and then it will stop working as an amplifier. So it is a performance metric for high frequency amplification. So if I need the very high frequency performance, for instance, in typically in analog radio circuits, then I will need very high FT values, and I will need to put currents. If we see, for instance, for very small currents here, the FT, it is just like tens of megahertz. Okay, 10 of megahertz here, we have 100 of megahertz here, we have 1 gigahertz. So if I need performance, then in the gigahertz range, I will have to put a lot of current. This is 100 microamps. If I have to go to dozens of gigahertz, I will probably have to put milliamps. And then something interesting is that since I am entering in the strong inversion, it doesn't grow at the same pace as in the lower side. It starts to plan out here. Start to do something like this, and actually it goes a little bit down later because we have the short channel effects. So this plot helps me to define what is the amount of current that I need to have a particular performance at high frequency. So I actually use this plot and the previous one. Both are very important. So we'll come back to the other here. So both are going to give me very important information in order to decide first the size of the transistor and second the bias. Okay? The size of the transistor will move this in this direction and this direction here, and the bias will give me also which points in this curve I can select. Now, how do I select the size and the bias? So there is a complete design methodology that is called the GMID methodology that is based only on these two plots. So typically I will need to accomplish some bandwidth requirements and gain requirements, and for that I will need to select the GM/ID that I want to use and also the FT that I need for my transistors. And we see that we mentioned before we will not want to work in very strong inversion in most of the cases. Sometimes we will be forced to, but most of the cases we will not want to do that. We will want to work actually in the lower part of this curve. However, in the lower part of this curve we have very low performance in frequency, so it may be that we cannot work in the lower part. So then we will be forced to move ourselves in this curve somewhere a little bit higher until we match the performance that we need in our circuits. So what we will normally do is to try to select the size of the transistor and the bias of the transistor that accomplish requirements on FT for our application, and that puts our point of operation somewhere above the strong inversion. Somewhere above the strong inversion, so that we have all the benefits for the weak inversion, that it is very good amplification, and at the same time we accomplish the frequency requirements, the bandwidth requirements. So we use both curves, and then that is the reason that why in our setup in Cadence I actually have let's plot it again, this one. Let me send it again. So that is the reason why I normally plot both GM/ID and FT versus ID, so that I can see both curves in the same plot. So that will help me to visualize very quickly what is the high frequency performance of that transistor and what is the gain performance for the current that I am applying. Okay, so we have GM over ID, we have FT. I can also plot GM here, and I can also plot the intrinsic gain. So what is the intrinsic gain? Come back here. So the intrinsic gain of the transistor, assuming that there is no capacitors, okay, we just have RDS, and then we have here VGS, and then GM VGS. Okay, so we have V out, and this is V in. So we have that V out divided by V in will be equal to minus GM times RDS. This is unloaded transistor, so that is what we call the intrinsic gain of this transistor, bias at a particular current. And this is also interesting. I can have the voltage gain of this transistor as part of my curve, so I will want to have actually these four in the same plot. So what we do is that we extract these four, and then we can plot them together. We can just put all of these ones logarithmic, this logarithmic, and then we split, and then here we put a vertical marker so we can track how the GM over ID and FT changes for different current, and we can see exactly how it changes, and we can also track the intrinsic gain. So we can try this for different sizes of transistors. As I mentioned before, increasing the width of the transistor will move these curves, or changing the length also will move these curves, and this will help us, these plots will help us very much to find the exact bias and size of the transistor that we will want to use. Okay, so you will make this template in Cadence as part of the elaboration number 1. So we have a summary. Subthreshold or weak inversion operation, we have a better GM over IDS. We avoid velocity saturation because we are handling small VGS voltages. We have a reduced excess of noise also, and we have that low biasing currents make it possible ultra low power operation, because in weak inversion we are talking about very small current that are necessary to put the transistor in weak inversion. The problem it is the speed. So the bandwidth that we can get, as we saw here, for very weak inversion, we really don't get the faster amplification, the faster frequencies. So we are working in radio applications, for instance. Most probably we will have to work in this area in very strong inversion. If we move here, then we will have to work here in strong inversion, which has very poor GM over ID, but on the other hand has the performance that might be required at higher frequencies. Okay, so the last part of this lecture will be our first amplifier configuration that we have actually talked a little bit. So we have the common source amplifier, and we can model it. We can model this amplifier. First, we have the schematic for large signal model. This is one way of implementing the common source amplifier. For an NMOS, we will have the connection of the source to ground, and then the drain with the load to VCC. And then we typically in integrated circuit design there will be a capacitive load. And we have input voltage here. Now we can have two cases here. When the source resistance it is not very large, we can assume that this is the best model. We have a voltage source and a resistance. If the source resistance is very large, it is much better to use the following model: input current and source current in parallel. From our circuit theory, we know that we can do this transformation from a Thevenin to Norton, so we can do the Norton conversion. It will look like this. It will be V in divided by Rs, and then we put the resistor in parallel, but they are exactly the same thing. So we have these two cases, and then now we can calculate the ABCD parameters at low frequencies. So at low frequencies we assume that capacitors do not exist, and then we have already done this for the voltage gain. The voltage gain here, if the capacitor doesn't exist, we call this parallel, this RL parallel with RDS, we call it out. And then we have that the voltage gain for this configuration is simple minus GM times R out. Okay, so that is the first one, and then that we calculate assuming that we don't load this with anything. So it is the output, it is open, it's an open circuit, so we keep it open. For the parameter for B, then we have the transconductance. We short circuit the output and calculate the current that passes here, and then we have at our parameter that dominates here, it is this transconductance here. Okay, so this is the transconductance gain, GM. So it converts all this voltage to current, and then we change the sign because we assume that the current goes, E out goes in the other direction. For the transimpedance, 1 over C, it is output voltage divided by input current. Then it is much easier to use the following model here. Okay, for this model, so we keep it the output voltage open, and then we just follow the input. So it will be E in times Rs. We have this voltage here. This time GM. It will create this current here, and then times R out. This has to be equal to V out. Also V out divided by E in, and that will be with the minus sign. That will be minus GM Rs times R out. Okay, and we can do the same for the current gain. The current gain, we short circuit the output, and we calculate the output current, and same thing, E in multiplied by Rs multiplied by GM, and all this current will flow directly to the output with different sign, and that will be equal to E out. Okay, so we have a E out divided by E in is going to be equal to Rs or minus GM Rs. So that is what we have here. And yeah, those are the gains, and remember that these gains are the opposite 1 over the ABCD parameters. Okay, so we can have characterized our transistor for this ABCD parameters for a common source transistor for low frequencies. Okay, now when we take into consideration the capacitance, we are going to start with without CGD. Okay, and without CGD, we're going to assume that our common source amplifier, okay, so as we saw this common source amplifier, the model here, it is a or model without intrinsic capacitance and resistances. Is just a voltage controlled current source. Okay, this is without the intrinsic resistances and capacitance. So it has an infinite input impedance, and it also has infinite output impedance here. Out also infinite because it's a current source, and then the input is input voltage there. Okay, so you go down here, and we can connect the input here, input source here, be in Rs. We have a total capacitance of the input. Okay, and then we have the following. We have CL and we have RL out here. So that will be the model for our amplifier. Okay, and then we can see that at the input, I am driving this with a voltage source. The voltage source, we have the following model, and then we take this voltage here, we call it V1. So we have a V1 divided by V in will be equal to C in 1 divided by C in plus R, and that will be equal to 1 plus G omega R C in. So it behaves like a single pole system, so it will introduce one pole. Nothing spectacular, nothing new there. The output behaves as a current source. The output behaves as a current source, so we can have something like this. Here out CL, and then we have that this output voltage be out, and we have this IS here, P out divided by IS is going to be equal to, and then we have out that it is in parallel to omega CL, and then it is out plus 1 divided by CL, and then we have V out divided by IS is going to be equal to R out, and that will be 1 plus G omega R out times CL. Okay, so we see that there is another pole appearing at the output with this value. Okay, so we have two poles. It's a two-pole system, and we come back to our model, model of our transistor. That it looks like this. Is RS, B in, CGS, then we have R out, on CL here, we see that there are 2 poles in this system. As you see, we call it B out. Here we have one pole that depends on the input resistance, source resistance, and the CGS, so this pole, and another pole of the output. So input pole and output pole. There. And that's it. We have these 2 poles, we have some gain. Now what we're going to do is to find a figure of merit. Okay, so we will define the figure of merit for amplification, that it is equal to how much amplification I can get at low frequencies, and then we have calculated that one here, divided by the product of the poles. Okay, so sorry, times the poles position. So we put the position of the poles here, and then we will have that when we multiply the low frequency gain and the poles, this will disappear here, and this RS is actually -1 here. So we will have the this is the transient frequency, approximately the transient frequency. So we will have at the gain at the gain times the position of the poles will give me this value, and this is a figure of merit. So what does it tell me? In order to increase this figure of merit, I will need to increase the FT of the transistor. Okay, the transient frequency of the transistor. I will need to put more current if I want to increase this one. I can also increase or decrease the load capacitance, or decrease the source resistance, but sometimes I don't have this as a parameters that I can change. So the only thing that I might be able to change is just to push more current in the transistor or change the dimension of the transistor. We can do the same exercise for the others. For instance, we have for the transimpedance amplifier, we calculated before the gain. Now we multiply by the poles, and then in this one we will have instead the following expression. Also, it tells me that if I want to increase this figure of merit, I will need to increase omega t, the transient frequency. We go to the transconductance gain. For the transconductance gain, we see that only the first pole is relevant because the second is short circuit. Okay, the second pole is not relevant when we calculate the gain. So only the first pole is the one that it is going to be interesting for us. So we multiply the transconductance by the position of the input pole, and then again we have expression that depends on the transient frequency, and the same for the current gain. Current gain multiplied by the first pole, this disappears, and then we have omega t. So the transient frequency is important. The transient frequency in the transistor is extremely important, because it will give me it will combine both the gain that my transistor can provide for a particular bias and how much bandwidth it can process, because that is given by the position of the poles in this system. Okay, so very interesting conclusion. The gain pole product give me a figure of merit of amplification and bandwidth. So we're going to use a lot this figure of merit very soon.